We're going to pick up where we left off yesterday with lesson 1.2 and finish some of the notes for that. We talked about domain and range previously, and now we need to continue on, and we're going to talk about increasing and decreasing functions first. So make sure you have your notes for 1.2 out, and we'll finish some of that stuff, and hopefully this will help you on the homework problems for 1.2. Increasing and decreasing function really have a lot to do with, if you understand positive slope and negative slope, then this really isn't very difficult for us. We have the graphs over here, increasing function, here's a decreasing function. It says a function f is increasing on an interval if for any 2 points in the interval a positive change in x results in a positive change in f of x or y. So we're basically talking about the change in y over the change in x being positive. So as you can see, we're looking at going up from left to right in general, which calls that the increasing. Here we're going down in general from left to right. Both of these, which are increasing all the time, we would say is increasing on the interval of negative infinity to infinity, all real numbers. So we would say increasing here from negative infinity all the way to infinity. Same thing with this one. This one would be decreasing from negative infinity to infinity. Constant is a horizontal line. If we remember back to slope, a horizontal line has a slope of 0, and therefore it's not increasing or decreasing, so we call it constant. And you can see some interval notation here for this one. We're under the assumption that there are some sort of arrows on the end of these things. So this is coming in decreasing until we get to a constant flat, and then we're increasing as we go away. So down here you can see decreasing from negative infinity to negative 2, and then it goes constant from negative 2 to 2, and then it starts increasing again. So it's all about what's the direction. Am I going down? Am I going up? Etc. Here's an example analyzing function behavior for increasing and decreasing behavior. First thing we have to do is graph it. I've got the graph of it over here. So you could type this into your calculator, this function g of x. Please make note that when you type something like this into your calculator, you need to do x squared divided by x squared minus 1, and you need to make sure that you put your x squared minus 1 in parentheses. Otherwise, your calculator will misinterpret what you're trying to tell it. And remember, it's really not the calculator's fault. It's more of operator error than anything else. It says tell when it's increasing or when it's decreasing. So what you're going to need to do first is graph it. Now, in order to figure out, we look at, there's clearly some asymptotes here, and we're not going to talk much about that today, but let's talk about the domain of this function. And that can help us out with what's going on here with what x can be and can't be. Remember yesterday we said that we can't take the square root of a negative number and we can't divide by 0. We have no square roots here, so that's not an issue, but clearly we have a denominator. So we would take, if we're going to look for the domain, we would say x squared minus 1 cannot be equal to 0. And if x squared minus 1 cannot be equal to 0, we could solve this two different ways. We could factor this as the difference of two squares into x plus 1 and x minus 1, or we could solve it the old-fashioned way. We could move the 1 over and say x squared cannot be equal to 1. And now when I take the square root, I would need to remember that x cannot be plus or minus 1. It would be positive and negative 1. And if you look over here, there's obviously an asymptote of some sort running in there and running in there. And those two things, that's going to be at x equals positive 1 and x equals negative 1. So you can visually see what the domain told us, that x can't be positive 1 and x can't be negative 1. Now, back to the domain, stating the domain. I know they didn't ask us that on this question, but this is good to review because it's going to come up a lot. It comes up a lot in your homework. I would say the domain of this function would be from negative infinity up to negative 1, and then negative 1 to 1, and then 1 to infinity. That's how we would write the domain of this function g of x. Everything except -1. I'm soft on the infinity end, so I have parentheses. I'm not including the negative ones here. I've got a union. Not including the ones there. I've got a union. Yesterday we also talked about range. Range we said we needed to get from the graph. I have the graph over here. Notice this has got it graphed up. You might have it as -10 of 10 and -10 of 10, and that's fine and dandy. If we wanted to go ahead and take a look at what's happening with the range, where are we non-existent? We have an asymptote here as well. It's going to look something like this. The asymptote here is actually at +1, which means we're going as high as 0, and then we're jumping all the way up to -1. There's no way for us to get the decimal in between there. So the range on the graph, how low do we go? We go all the way down to -infinity. We come all the way up to 0, and notice 0 is included there. We can be 0, so we are strong on the 0, which is a bracket. Union, we start up again after we jump all the way up to +1 on the y's. But we're not including the y's because these asymptotes are going to get really close, but they're never actually going to get there. So I'm going to go from 1 to infinity. So a little recap of domain and range from yesterday before we get into the interval of increasing and decreasing. Let me get rid of that asymptote. Where did it go? Whoa. Intervals of increasing and decreasing, which was what we just kind of took a look at. We're going to be going from -infinity. So again, when we're in interval notation, we're talking about what's happening as we come in from over here, and we're clearly going up. We're going up, even though it looks like it's leveled off, it's not. We're going up. And we're going to go up until we get to that -1 because of our domain idea. So I'm going to say I'm increasing here from -infinity all the way up to -1, and I'm soft on the -1 because I never actually get there. And then I'm going to jump over the -1, and notice I'm still, when I'm coming back in here, I'm still coming up all the way up to 0. So I'm going to union with -1. I jump right over it, soft on the parentheses, and I come up to 0, and we'll say the 0 is included there. 0 is kind of a transition point. It's actually a local maximum, which we'll talk about in a minute. And then after we turn the corner at 0, we go to decreasing. So when we write our decreasing, we're going to start decreasing at 0. We can go hard on that as well. And then we'll go up to +1, and we will union, and we will jump. Again, we jump over, and now we're going down from +1 to 0. So again, +1 to infinity. Let's make that look like an infinity. Again, we're talking about the x values. So from when the x's are from -infinity all the way up to 1, I'm increasing. I jump over the 1, I'm still increasing to 0, and then I start decreasing, jump over the 1, and start decreasing there. So my -1 and +1 really has a lot to do with my domain. It also has a lot to do with the increasing and decreasing in this case. Bounded above and bounded below. You have seen things bounded above and bounded below. It's as simple as, do I go up to infinity or don't I, is really what we're talking about. It says a function f is bounded below if there is some number b that is less than or equal to every number in the range of f. Basically, there's a lowest value that we can find. Any number such b is called the lower bound. So a very simple example of bounded below is y equals x squared. You know that that looks like this. We have a definite bottoming out point, which would be the lower bound. We have other functions that might look like this and be these ugly things, but hey, there's a definite lower point, and that means it's bounded below. Bounded above means we have a high point, so it might be a parabola opening downward. If we're bounded above, we have a definite upper bound right here. Again, it might look like this, and be all funky, but I have a definite top. I do not go up to infinity. I have a maximum value, and that means bounded above. A function that is bounded, and we'll look at a couple of them in 1.3, which you're going to take a look at. It might have an asymptote running here and an asymptote running here, and then it kind of does this little S-curve guy and never gets above the upper asymptote, never gets below the other one. So we'll look, it does not go up to infinity and it does not go down to infinity, to negative infinity. It does some different stuff. And that's called bounded. That means it's bounded both above and below. Y equals x cubed looks like this. This is not bounded above and not bounded below. It goes up forever, it goes down forever. There is no maximum or no minimum point that we can locate because we're going to infinity. Okay, so bounded, a definite bottom is bounded below, a definite top is bounded above, which brings us to maximums and minimums. We should have seen maximums and minimums a little bit in Algebra 2. Local maximum, local minimum, absolute maximum, absolute minimum. It will have an absolute minimum if it is bounded above. If it's bounded above, it has an absolute maximum. If it has a bounded below, it has an absolute minimum. So if I was to draw something like so, and say this is the function that we came up with, first of all, this is clearly bounded above, and the highest point is going to be the absolute max, and that would be right here. This would be called a local minimum, or a local maximum, excuse me, a local maximum. And what we can do is we could go ahead and we can find our area that we want to kind of say, I want to find the highest point within there. And since we have a rounded off point, that's what's considered a local maximum. So local max isn't the absolute, it's not the highest point. The absolute max is way up here. Notice right here, right there, I have a local minimum. I have no absolute minimum on this one. Why? Because I'm not bounded below. You have to be bounded below in order to have an absolute minimum. Since I'm going down forever, I just have a local minimum in between there. We have the lowest value. We have a hump. Anytime you got a hump, you got some sort of maximum or minimum. And we got an absolute if we're bounded above. We got a local here. We got a local there. Please note that your book sometimes calls your local extrema relative extrema. That means this could also be called a relative maximum. This could be called a relative minimum. Those are just interchangeable for our maximum and minimums. Get your calculators out because we're going to need to figure out how to calculate these things up. I've got a picture of f of x equals x to the fourth minus 7x squared plus 6x. This should be on your note sheet. So the first thing you should do is graph that. X to the fourth minus 7x squared plus 6x. I've also got a picture of the graph here which has the absolute minimum done for us, but we've worked with the calculator here a couple of days. The first thing that you're going to need to do is graph it, and then you got to go to the window. And you got to go to the window, and then you got to be able to see what's happening before we head to the infinities. We've got a little cheat here because we know we're going to go at least as low as negative 24. So the window, you want to make sure that your window fits this thing in there. So your x max and x min, I'm not sure if this is negative 1. If this is negative 5 to 5, you can probably get away with x's from negative 5 to 5, but you may have to make them bigger. Negative 10 to 10 is probably fine and dandy. My minimum, or my y's, my minimum needs to be at least negative 25 so that you can see it. So if you can't see where your max and mins are occurring, you're going to need to adjust your minimum and maximum in your window. So always go to the window so that you can see the kids across the street fighting with one another. So set your window, and then if you can identify, you can clearly see I've got an absolute minimum, I've got a local maximum, and a local minimum. I've got three things going on. So you need to go to calculate, which is second and trace, I believe. Go to calculate, and then you have a max or a min. So if we want to do this absolute that we have the answer to here, if you want to do that absolute minimum, you're going to go to calculate and then go to minimum. And then you need to take the spider function, and then you need to just go left until you get to left of that minimum. So go to where that spider function is, I don't know, right in this area. And then it gives you the little cue that says, okay, I'm on the left side of it. And so first you go to the left bound, and then hit enter, right? And then you go to the right bound, so you scroll that puppy to the other side till it's like right there. And now it's asking the question, would you like me to guess the answer? And you tell it no, silly calculator. I would like you to tell me the actual answer, and you hit enter. And you should get exactly what we have up there, assuming you've done it correctly. Negative 2.05. So let's go with 6.5, sure, whatever, and negative 24.057. Okay, you're going to repeat the process. So now you need to find these locals. So you're just going to go back to calculate, and now you're going to do a maximum here, and you're going to surround it. So get the spider so it's like over here, and it'll give you the high point. And then you're going to go do another one, and you're going to do calculate and minimum, and now we're going to get it surrounded here. And so get the function into the y equals graph, calculate, left bound, right bound. So if you're thoroughly lost, you could certainly go back into the Schoology, play this thing again, and you're really just entering in the function, making sure that you can see the graph, and then left bound, right bound for your max and mins. So your end result here's the total solutions. It says local minimum well, actually that's an absolute minimum. This should say absolute. Negative 24.06, that's the minimum, and it occurs at x of negative 2.06. We have another minimum of negative 1.17, and it occurs at x equals 1.6. So here's x equals 1.6. There's the ordered pair, 1.6 and negative 1.77. The local maximum, which is right here, it's a max of 1.32 and occurs at 0.46. Notice this is bounded below. It's bounded below and therefore has an absolute minimum. It goes up forever, so that's why we only have local maximums. We can't have an absolute maximum. Last two things on 1-2 are whether or not a function is called odd or even. Odd or even. When we think about even functions, we want to think about the graph of y equals x squared. It's a parabola. It opens upwards. It has symmetry with respect to the y-axis. I can draw a line down the y-axis which cuts it into two halves. Okay? How do we calculate whether or not we have an even function? When I change all of the x's to negatives and simplify, I get a function back that is exactly the same. F of x equals f of negative x. So if you take this function right here and I calculate f of negative x, that would tell me to put a negative in for all of the x's. And now when I simplify, a negative x squared, when you square a negative, you get a positive. And lo and behold, when I change it to a negative, I get exactly the same thing. Therefore, f of negative x is equal to f of x, and thus we have an even function. That is when you change everything to negative. So if it's not even, what does it need to be? Skip this one for a second and go straight to odd. If it's an odd function, it will resemble something like y equals x cubed. Here's the graph of y equals x cubed. It has symmetry with respect to the origin. That is, it can be rotated 180 degrees around the origin, and we end up looking exactly the same. If you're not sure, take your computer, flip it over, and you'll see exactly the same graph upside down. Don't actually do that. When we have an odd function algebraically, and we change all of the x's to negatives, the function ends up being exactly the opposite. So I start with f of negative x. I'm going to put a negative in for that, negative x cubed. I cube a negative sign, I get a negative sign, and I get the opposite of x cubed. What did I really end up with? I ended up with the opposite of the original function. The original function was x cubed. I ended up with the opposite of it. That's how we algebraically show that something is an odd function. An odd function. So if you're asked in your homework to check to see whether or not something is an odd function or an even function, for example, you're going to say, tell whether it's odd, even, or neither. Odd, even, or neither. And it gives you a function. Say it gave you f of x equals x squared plus 3. In order to check, I change it to an f of negative x, plug it in, and I get negative x squared is x squared plus 3. Well, I put a negative in there, and I got exactly the same thing, and therefore it has to be even. This was the original function, and since f of negative x is equal to it. Does it have something to do with an even exponent? You're darn right it does, because if we took a look at another example, same thing, and said f of x equals 2x cubed minus 3x, check to see if it's odd, even, or neither, plug in negatives, plug in a negative, and I get negative x to the third will give me a negative x to the third. A negative times a negative is a positive. Notice I went from my original function, changed from a plus to a minus, changed from a minus to a plus, which means I really could factor out a negative sign, and I'm right back to my original function, which tells me that f of negative x is equal to the opposite of the original function, and therefore we are an odd function. What's an example of one that would be neither? I can do one of those for you. What if we had f of x equals negative 2x cubed plus 4x squared? How do we check? We've changed them all to negatives. Negative 2 times negative x cubed plus 4 times negative x squared. So I get negative 2 times negative x cubed, which is going to turn that negative. This will be a negative times a negative, which is a positive x cubed. And now when I square this negative sign, it goes away, and I end up with plus 4x squared. Well, I started with negative 2x cubed, and I ended with positive 2x cubed. I started with positive 2x cubed and ended with positive 2x cubed, which means we didn't change all the signs. We didn't turn into the opposite, which would be odd, and we didn't always stay the same, so this would be neither. Neither. That's an example of even, odd, or neither. And you can take another look at one of those examples. Otherwise, we'll talk more about that, I'm sure, when I get back. The other one that I skipped over, symmetry with respect to the x-axis. Is this a function? And at this point, you should collectively all wake up and say, no. How do I know that? I can run the vertical line test very quickly. Right through here, I hit two points. I'm no good. We have 4 is paired up with -2, 4 is paired up with +2. Can't have the same x get two different y's, just doesn't work. But this is how you graph something with respect to the x-axis. It gets, we can run a line through the x-axis that cuts into two mirrored halves on the top and on the bottom. So I'm more concerned with you understanding even and odd, but please understand that the x-axis can also we can have symmetry with the x-axis as well. That does it for lesson 1.2, the functions and their properties. Hopefully you didn't fall asleep. Hopefully you can now work further on your 1.2 homework, which we have a quiz on 1.1 through 1.3 next Tuesday. Enjoy.